So in this video, I'm going to go over some sample size calculations for case control studies and go over an example. So this is the general formula. It looks kind of complicated, but I'm going to go over what each of these things mean. So what this will spit out at the end is the number of cases you'll need, and bear in mind that a study, like a case control study, is composed of both cases and controls. So once you know the number of cases, you're going to have to also figure out the number of controls you'll need for a total, and I'll show you that in a second. But the two values that are the easiest to find, that are the most constant, are Z alpha, your confidence, and Z beta, your power. 95% confidence is conventional, so 1.96 is almost always what we put here. And 80% power is also conventional, so 0.84 is almost always what we put here. These other terms, P here is the prevalence of exposure in the population, R here is the ratio of controls to cases, and that's how, once we find the number of cases, we can determine the number of controls we're going to need. And D here is the magnitude of difference we want. It's a difference in proportions, and I'll go into a bit more detail in a second how we find that. So this example I came up with is a case control looking at smoking and lung cancer. We want 2 controls for every case, and we want to find the sample size necessary to detect an odds ratio of 2 in a population where the smoking prevalence is 8%, and we want to have 95% confidence and 80% power. So pulling information out of that, we have Z alpha and Z beta, because we know the confidence and power. We know the ratio of controls to cases. That's something that we choose usually. The prevalence of the exposure is 8%. We don't have an obvious value for D here, but we do know that D is the magnitude and difference we want to detect, and it's a difference in proportions. We have an odds ratio here, which is a relative value rather than an absolute value, as in like a difference. And I'll show you what I mean by that. So D here is the difference between the risk of exposure in cases, or proportion of cases exposed, minus P naught, which is the risk of exposure in controls, or the proportion of controls that are exposed. So this is a table that is pretty common, where it's just a 2x2 here, where we have case control by exposure positive and negative. So to figure out the proportion of exposed cases, P1, we can take the number of exposed cases, A, over all the cases, so A over A plus C, and P naught here, the proportion of exposed controls, we can take the number of exposed controls, B, and divide by all of the controls, B plus D. Yeah, so these two formula, you're typically left with like a 2 equations, 2 unknowns situation here. And what I mean by that is we know P and R, and we know the odds ratio here. So in this situation, we have 2 equations, and in both of them we have P1 and P naught that are unknowns. Something you might remember is, in this situation, we typically solve for an unknown here, which is already done. We solve for P1 and sub this whole value in for P1, but that is very cumbersome here. What we can do instead is make an assumption that P is a good approximation of P naught, and that's typically okay in case control studies, and I'll get to that in a second, because that is essentially true whenever the disease is super rare, and that's usually why we do a case control study in the first place, is when the disease is super rare. And to get into why P naught and P are pretty equivalent, P naught here, the proportion of controls that are exposed, so B over B plus D, and P is the overall exposure, so everyone who is exposed, A and B, over everyone, so A, B, C, and D. But if the disease is super rare, then A and C are kind of negligible in comparison to B and D, so we can almost cross out A and C, and we're left with B over B plus D. So yeah, that's so in there's a pretty much most of the time in a case control study, we can make this assumption that P and P naught are very similar, at least for the sake of sample size calculations. So once we do that, then we don't have a 2 equations to unknown situation anymore. We have just one equation with one unknown. So we have this equation here, and we know the odds ratio. We know it's 2. We know that P naught is a good approximation of P, so P naught is 0.08, and plugging and chugging, we end up with a P1 of 0.015, which we can plug back in, or sorry, we don't need to plug it back in. We know P naught. So yeah, we have the information we need to find D. So we had 0.015 as P1 and P2. I guess I should have put P naught. But yeah, so, and 0.08. So plugging all of that back into this equation, so P here we have 0.08, 1 minus 0.08, and 2 plus 1. D here is 0.07, we found before, and 2 here for R. Once we plug all that in, we come out to a number of cases as 177. But like I said before, that's the number of cases, and that's not the total of the population, so we know we need 2 controls for every case. So 177 multiplied by 2, just wanted to make sure. Yep, 354 controls, and when we add those together, we get 531 individuals that we'll need in total. Just some other things. It's also common to have a number of people and want to know the power that we have. So what we can do is basically rearrange this to solve for z beta, and if we solve for z beta and we get a z beta value, let's just say we get a z beta value of 0.84, then we can use the z table and find 0.84. So this is the second digit here, and this is the first digit, so 0.84. That is 80% power, and that's basically how you do that. You'll notice that the formula I showed, P, P1, and P naught, all kind of rely on this idea of a dichotomous exposure, where P1 is the we have exposed cases and exposed controls. There's not in proportion of exposure overall. There's no opportunity. It's exposed and not exposed. There's no opportunity for, say, like a medium level of exposure or a continuous exposure. But that's a very common thing to want to investigate. So what do we do in those situations? Well, this is an example where this is just the height distribution in our population, and let's just consider it normal like this. If we were to want to do sample size calculations with an exposure like height, something we could do is just find the distribution for the population and cut it in half, and say everyone above this like median value or mean value is exposure positive, and everyone below it is exposure negative. And now, like I said before, P naught, the proportion of controls exposed, this controls, they represent our underlying population anyway. So we can assume that about half of the controls are going to be exposed because half of the population is exposed. We made that happen on purpose, that it's 50-50. So we can say about half of the controls are exposed. We might be interested in separating height into quartiles here, and in that case, which 2 do we compare? Because we still need to boil it down to 2. It's best to pick the ones with the strongest contrast. So we pick the 4th quartile and the first one. So notice what happened here is when considering the entire population, this 1st and 4th quartile make up 25% of the population each. But as soon as we eliminate this middle part, now this first quartile represents 50% of this population, because now our population just consists of this quartile and this one. So in that way, P0 still represents 50% of this population being exposure positive, being 180 centimeters or above, while exposure negative is less than 160. But notice that this calculation only included, like, it excluded everyone that's between 160 centimeters and 180. So we need to consider that, where, let's just say, using this, we found we need 500 people. Well, we need 500 people to find this contrast, but if we're interested in also including these people, we need to recognize that that was only 50% of the population. We used this quartile and this quartile for a total of 50%, but this 50% was missing, so we need to double the sample size we found. So if here we found we needed 500 people, we need to double that to 1,000 to be able to capture the people here. Another situation that gets more complex is, say we have like a 3-level exposure here that's not as evenly distributed. So we have 50% of people that are low exposure, 30% that are medium exposure, and 20% that are high exposure. Again, we're gonna boil this 3 down into 2, and we're gonna pick the largest contrast. So we're gonna compare the 50% and 20% group and pretend this medium one doesn't exist for now. So now we're expecting that our controls are going to have this distribution, because this is this distribution here is in our population. So the proportion, we're considering this exposed, the proportion of this population that is exposed, of this new population that only includes low and high, 20% over all of it, so 20% over 20 plus 50 comes out to about 30% of the controls, which is synonymous with our general population being exposed. So now we have a P0 and we're able to solve for the rest, but we got to recognize, like before, that we only use this 50% and 20%, so we only use 70% to find this calculation, but we're likely interested in including this middle layer, so we need to account for the fact that we only budgeted being able to detect this in 70% of the population, but we want to find it in 100%, so we figure out what our total sample size would need to be if we were to consider that this was only 70%. So we do that by dividing by 0.7. It's basically saying, like, what is it? 500 divided by what is 70%. That's basically what this was rearranged to, and the what was 715. So if 500 is 70% of something, we figured out that something is 715. So that's what our total population would need to be. Another thing I wanted to mention is that if you have strong confounders that weren't part of this calculation, a kind of arbitrary rule of thumb is to inflate the sample size required by 10% per strong confounder.